Thank you, Orna, and thank you, Samuel, for organizing this gem of a grow. So these are my co-authors. Co-authors of the new results, because like Honza, I couldn't resist having a majority of the talk devoted to motivation and survey. But if you have heard me speak about this before, please don't be impatient. At the end there are new results and I think nice questions, so bear with me. The problem is about partitioning graphs, and here is a kind of an outline of my talk. So I'll be talking about graphs and then restricted graph classes and about problems about algorithms and about characterizations. And the 1, 2, 3, 4 is the order in which this happens. Okay, so what kind of graph partitions? I'm partitioning the vertices, and there are restrictions on the vertices and or the parts and their connections. So the parts can be restricted to be either an independent set or a clique, or not restricted, and similarly connections, the constraints between the connections between parts can be there are no edges between them and there are all edges. So how to formalize a partition like that? Well, you can draw pictures, and I'll draw pictures most of the time, but I guess it's convenient to have some kind of notation, so I'll take a matrix, and I have a fixed number of parts. This is an important part. I have a fixed number of parts, and so this is a fixed size matrix, and the diagonal entries describe the connection. The diagonal entries describe the quality of the parts, and the other entries describe the quality of the connections. So formally, then I have a partition into k parts for a fixed matrix of size k, and the ith part is a clique if the diagonal entry is 1, and is an independent set if it's 0. And if I haven't restricted it, I put an asterisk there. Okay? Similarly for connections between parts. And the problem is my matrix M is fixed, and you want to know whether the input graph G has an M partition or not. So here is an example matrix. The diagonal entries are 0, so I have 3 independent sets. White circle means an independent set. And the other entries are last, there is no restriction, so that's a green line, no restriction. So of course this is the problem of 3-colorability, and therefore matrix partitions generalize colorings. What if I have another entry here, 0? So there can be no edges between color 1 and color 3. But each set is still independent because I have diagonal 0. So this is the same problem as, is there a homomorphism to a path of length 2? Such a mapping is a homomorphism. So M partitions generalize homomorphisms. Notice that so far I haven't seen a 1. I only use zeros and asterisks in my examples. So what happens when I introduce a 1? Let's put a 1 here, for example. So a part that's 1 must be a clique, and I denote that by a red circle. So I have here a clique, I have here an arbitrary connections, and these sets are arbitrary, right? There are asterisks on the diagonal here. So of course if I have an asterisk on the diagonal, the problem is trivial because I can put every vertex in that part is unrestricted. But for this problem it's interesting to add an additional restriction that each set is non-empty. And if you read then what this means is you want a clique whose removal disconnects the rest of the graph. So this is the problem of a clique cut set. So I have just mentioned one variant of the problem, which is you have non-empty parts. So the kind of homomorphism, the mapping underneath it is surjective. You might talk about digraphs instead of graphs. The matrix then is no longer symmetric. You can add lists to vertices, just like in a list coloring or list homomorphism. Each vertex comes equipped with a list of parts in which it can be placed. Or you can talk about more general versions of the partition problem in relations which are more general than binary, but I will not do that in this talk. So a couple of examples that occur. You see partitions of this sort often in the study of perfect graphs. Here are two examples. Here you want to partition your graph into two parts. One is a clique, one is an independent set, and nothing in between, right? And here you want to, this will be a subjective problem. You want to partition your graph into four sets that are arbitrary but not empty. And between these two sets there are no connections, and between these two sets there are all connections. So this is the problem of finding a skew cut set for a graph. And that problem, it turned out to be progress in this problem turned out to be crucially using the fact of introducing lists. So this problem, Chordal asked the complexity of this problem in the 70s, and it stood open for a long time, and then we formed a kind of version with lists, and we found an easy quasi-polynomial n to the log n type algorithm, and eventually led to some improvements in the complexity of the algorithm. Eventually, using the lists, this was proved polynomial. All right, so this is the basic problem. You have a fixed matrix, and you want to know whether the corresponding partition problem is polynomial or NP-complete. We are in region 1. Even if the matrix has no ones, we don't even know whether the answer here is always one or the other. This is the dichotomy problem of constraint satisfaction. In the situation of directed graphs, if the graphs are undirected as I formulated it, in fact, we know that this is polynomial or NP-complete according to whether the graph is bipartite or not. Now, what we were able to prove in the general context of n partitions is the problem is always either polynomial, either NP-complete or quasi-polynomial, solvable in quasi-polynomial time. Now I'm moving to region 2 in my survey overview. If you look at restricted graph classes, you may want to start, say, with perfect graphs. You know, the chromatic number of perfect graphs can be computed, the colorability can be tested in polynomial time. How about n partitionability? Well, the situation here turns out to be as bad as possible. So this problem, if you could decide this problem, if you could decide for every matrix M whether the n partition problem restricted to perfect graphs is NP-complete or polynomial time solvable, you would be solving the dichotomy conjecture that I mentioned earlier, that is an open problem because of this result. For each constraint satisfaction problem, there is a matrix M which is polynomially, whose n partition problem is polynomially equivalent to the CSP problem. So if you, here is, I think, statement of what I mean by that. So if we could decide this question, if we could even say yes here, we would have solved the problem. So even perfect graphs seem very difficult to handle. All right, if we narrow our focus a lot, let's just say look at cographs, then of course it turns out to be solvable in linear time. And here is, I'll say the word width, because if you have bounded clique width, then you can solve this problem in linear time. You know, the partition can be described in an SOL. Now, how about Chordal graphs? This is what I'm focusing on here. Well, for chordal graphs, again, we know chromatic number or K colorability and coverability by K cliques can be solved by easy linear time algorithms. How about just M partition problems in general? Well, this is colorability. This is covering by cliques. This is covering by prescribed number of cliques and independent sets, also polynomial, so things look good. So this whole, can we solve all M partition problems in polynomial time? Homomorphism problems, by the way, I didn't make a page for that. Homomorphism problems can, similarly to coloring problems. So let's look at the first interesting case. Zeros on the main diagonal. We'll use the word width for the second time because a chordal graph that has a partition like that must be coverable by 5 cliques, so it's 5 colorable, and the maximum size clique is 5, not coverable by 5 cliques, I'm sorry, coverable by 5 independent sets, so maximum clique size is 5, and chordal graph maximum clique size of 5 is bounded tree width, so this is easy. How about this one? This was the case I was discussing before. Here you have covered by 5 cliques, so maximum size independent set is 5. Maybe it's not so transparent, but we have an algorithm, a polynomial time algorithm for this. All right, there is actually a class of matrices I would like to describe. How am I doing on time, Lorna?
You have another 10 minutes.
So I have used up more than half of my time.
10 minutes and then questions.
Okay. I'll go maybe quickly through
15 minutes.
This is a graph class. This is a class of matrices which includes all the polynomial cases that I have covered and all the polynomial big classes of examples we know. So maybe it's worth describing the matrix. So I'm discussing the version without lists. I'm discussing the basic version if I haven't made that clear. So the diagonal will have only zeros and ones. You want to partition into some independent sets and some cliques, and the other connections are kind of arbitrary. But you can divide your matrix into a block with 0 diagonal, a block with 1 diagonal, and then these two off-diagonal matrices. I put this off-diagonal matrix in red because the definition of being a cross matrix actually only talks about this red matrix. And the condition is, to be crossed, is each 0 and each 1, each non-asterisk, lies in a row or column of non-asterisks. So for example, this column and these two rows cover all non-zero entries. So this is a crossed matrix. This is also a crossed matrix. This matrix is not crossed. This 0 you cannot cover by either its row or its column. This matrix is crossed. The red matrix is empty. The red block is empty. So it trivially satisfies that. I mean, this matrix is crossed because there are only asterisks. Again, trivially a cross matrix. Okay? So the fact is that we can prove that if the matrix is crossed, then the M partition problem for chordal graphs is solvable in polynomial time. And this includes all the examples that I have previously described. But we have also found non-crossed matrices for which the partition problem is NP-complete. Unfortunately, we know it's not true for all non-crossed matrices, but there exist non-crossed matrices, and that matrix problem is NP-complete. So the answer to our original question is no. And we don't know which matrices have polynomial and which matrices have NP-complete and partition problems. This is region 2. An open question here is to decide what makes a matrix polynomial or NP-complete for chordal graphs. All right, so I have another column there of characterizations. What do we mean? Well, think of 3 examples. The M partition problem for something like 3 colorability turned out to be NP-complete. The n partition problem for something like bipartition, two-coloring, is polynomial solvable, but there are infinitely many minimal obstructions, like odd cycles. Or there could be a finite set of minimal obstructions. For example, for a matrix like this, we think this is the split partition, is the graph. A split graph has a well-known set of 3 forbidden induced subgraphs. So therefore we have new hope now. We are moving to region 3. Maybe we can at least look at a matrix and decide if it has a finite number of minimal obstructions. And here's a picture of NP-complete matrices with NP-complete problems and matrices with polynomial problems or other problems. We don't know whether there is even a fixed boundary there, and if there is, whether all the other ones are polynomial. This is kind of wound up in foundational problems in theoretical computer science. But the distinction between there is a finite obstruction set or there is no finite obstruction set, that's really, there is a boundary, and maybe it's not so jagged, and maybe we can say something about that. So I'm in region 3 now. It turns out that if your matrix has 2 diagonal zeros with the corresponding entries asterisk, or 2 diagonal ones with the corresponding asterisk, then the problem has infinitely many minimal obstructions. You can think of non-bipartiteness. We actually use high girth and high chromatic number to construct these infinitely many obstructions. So we call those matrices unfriendly, and we would like to know whether friendly matrices have finitely many minimal obstructions. And it turns out to be true up to matrices of size at most 5. But on size 6 we already found counterexamples. So this being friendly or unfriendly has something to do with it, but it's not the answer. There are both friendly and there are both finitely and infinitely many minimal obstructions for friendly matrices of larger sizes, and so in region 3 we still don't know the classification. We don't know the answer. All right, so now I'm moving to restricted graphs, and how am I doing on time? This is the new work. I still have 5 minutes, 6 minutes.
You do.
Good. Okay. So for perfect graphs, it only takes a moment of reflection to see that actually there's just one forbidden minimally induced subgraph. So I'm talking about homomorphism problems, right? If the matrix has no 1, these are the homomorphism problems. There is always just one forbidden subgraph. Now, for perfect graphs, where Chordal which include Chordal graphs, there is another kind of description of a class of matrices for which finiteness of the number of obstructions is guaranteed. They are all included in the crossed matrices. So to remind you of the block partition here, although the matrix that was red is now green, what we want of a normal matrix is that in each region the non-diagonal entries are all asterisks or all non-asterisks. So in particular a normal matrix is crossed. And so what we were able to prove is for perfect graphs, if the matrix is normal, then you get automatically a finite number of obstructions, finite number of minimal obstructions. So for cographs, in fact, there are always finitely many minimal obstructions. And let's move on to Chordal graphs. All right, so here is a matrix that we know is polynomial. Does it have finitely many obstructions? Actually, I meant to ask Lorna whether this follows from their algorithm. We had a different algorithm for solving this problem from which is a certifying algorithm, and at the end we can find an obstruction, and it turns out there is a unique obstruction. So this generalizes the kind of minimal obstructions for coloring and covering by cliques There is just one minimal obstruction for chordal graphs, partitionability into a fixed number of cliques and fixed number of independent sets. So that looks good again. Maybe we can say now in region 4 which matrices yield finitely many chordal minimal obstructions and which lead infinitely many, and just in case you fall asleep between now and the end, unfortunately we don't know. The answer will be, this is an open question I'm posing. But let me tell you what we have done looking at small matrices. A student worked for a master's thesis on classifying all matrices of size up to 4. And so if you look at a 3 by 3 matrix, say, with just 0 diagonal, then you might say, okay, if they're all asterisks, I know the answer is finitely many. If they're all non-asterisk, I know the answer is all finitely many. So let's say this one is asterisk. And if this one is asterisk as well, first case, then if this one is 0, this we have seen before. Here we have 2 identical rows and 2 identical columns. I really just want one independence and then another independence set with arbitrary connections between them. So this is bipartitionability, which for chordal graphs has only one minimal obstruction. So this is one interesting matrix. And by a similar analysis, in the other case, you get this as a. So overall, there will be 8 interesting cases, not excluded by the previous results. And in each case, we get an interesting theorem. So I'll describe in the remaining few minutes 2 examples of such results. Here is the first one, maybe the most interesting, surprising, and also easiest. They turn out to be matrices which have infinitely many chordal minimal obstructions, which is not so surprising knowing that there are matrices which are NP complete. But we are talking about size 3 by 3 here, right? All right, here is the example. I wanted to partition one of the 2 examples. I want to partition into 3 independent sets, such that sets 2 and 3, say, have all connections between them. This is a complete bipartite graph. And now, I think about chordal graphs as not allowing minimal obstructions of the type of odd cycles, right? Parity, using parity for colorability as an obstruction to colorability works because I have these odd cycles, but chordality prevents that. So here is a way to get around chordality so that you can use parity. And I have to say that these are the only infinite families of examples we know for any matrix. But of course there must be other ones because the problems are complicated, NP-complete problems and so on. So why do an even path with the apex vertex which omit the last 2 points, why is that not partitionable like this? Well, you can easily conclude that this vertex cannot come here because then the path would have to zigzag here and you get 4 cycles in no time. Right? So the path cannot zigzag here. So this vertex must come into one of these sets. Suppose it comes here. Then the path is easily seen. You have to zigzag here with your path. And both the non-connections must end up here. But the parity prevents that. One of the endpoints will end up here, and then you'll have the connections which you shouldn't have. Once more, this vertex must end up here by symmetry. Then the path has to zigzag here, and so both of these endpoints cannot end here by parity. One must end here, and you would get this connection which you don't know. All right, well, this was the easiest. Another example, there are 2 like this, where you actually can get the obstruction. So here is one interesting theorem. You can partition your chordal graph according to this matrix, into this picture, if and only if it has no induced subgraph like this. And in this example, and this is not difficult to prove, if you don't have these, then you get some structural description of what the graph must look like, right? It cannot have it can have a K4. If it doesn't have a K3, then you just use these parts. Make it bipartite chordal graph. So you put it here. If it has a K3, then every other vertex has at least one connection, and so on. And you see easily that it has a partition like this. There are 2 examples that are easy like this. Then there are 2 examples that are a little bit more difficult, typified by this. And I have to explain what these obstructions with labels means. mean? This is a minimal obstruction provided this vertex goes to part 3, which I believe is this part. This is part 3. Okay, and how do we use that? Well, I know there are no 4 independent vertices. So if there are just 2 independent vertices, I can cover it by 2 cliques and it lies here. So therefore the size of the largest independent set is 3. At least one of those 3 vertices then must get color 3. And so any obstruction will have something small to prevent A from being color 3, something small to prevent B from being color 3, and something small to prevent C from being color 3, and putting that together means that you have a small obstruction. So the number of, or the size of the minimal obstructions is bounded. And then there are 2 other examples which are unfortunately more complicated, 2 other matrices which are more complicated, and for those we only put a bound on the size of a minimal obstruction. So we haven't found really a universal approach that works for all matrices, and we don't know which matrices give finitely or infinitely many minimal obstructions. I think it's an interesting problem. And to conclude, I just thought, well, here's an open question that maybe you can answer easily. Can we at least say whether there are more matrices that have finitely many or more matrices that have infinitely many minimal obstructions? I think that should be answerable. As an example of matrices that have only finitely many minimal chordal obstructions, if you don't have something, like if you don't have a 1 or if you don't have a 0, we know all those have finitely many, so that's already, a good number. Maybe not a big number, but a good number. We can also generalize the 2 examples that had infinitely many minimal chordal obstructions, and we generalize them in a way that the same obstructions were. And here's a kind of a picture suggesting what that looks like. So the 0 block is itself divided into 2 parts, and the 1 block is divided into 2 parts. This is the, I guess, 1 minus the identity matrix in each case. These are completely arbitrary, except I want at least 2 asterisks. These full ones, diagonal of ones. So there's lots of free entries. These all entries are completely free. If you look at it, you see there is slightly more than half of the entries which are completely free. So then you get at least square root of the total number of matrices with prescribed k and diagonal entries will have infinitely many minimal obstructions. But that's far from answering the question that I wanted to answer. Finally, my last open question is, looking at the examples, after all we did those 3x3 matrices to find some inspiration of making guesses for general matrices. When the diagonals are 1s, this seems to be an interesting case, which is hard, and in all cases that we looked at, they had finitely many minimal obstructions. So I'm not formulating this as a conjecture, but more as a question. Is it true that if you have a matrix whose diagonal is 1, you want to partition into cliques with some additional restrictions, the number of minimal obstructions is always finite for chordal times? We don't know the answer to that.
Thank you.